Hi class, so today I want to look at the z-score, standard error, and the normal curve worksheet. So this starts on page 43, right, if you're following along. So here we're told, so the histograms we created earlier are discrete versions of idealized continuous distributions, such as the following normal distribution shown, right? So before we looked at a normal distribution, and remember when we create a histogram, if the bars get really, really small, right? So remember the kind of the idea is that this is still a histogram, right? We have just really small bars, right? So the smaller and smaller that we can make these bars, oops, well, blue on blue doesn't look good. Let me pick a different color, right? So like there's some histogram bar from here, here and so forth, right? So all of these would have some kind of histogram shape. And as we make these bars smaller and smaller and smaller together, eventually it'll create this smooth curve, right? So we might originally start out with bars that are this wide, right? And then, get maybe a little smaller bars, and that'll change what our shape looks like, right? And then keep getting smaller and smaller, and then we can get these curves. Right? And we looked at distributions before also in chapter 1, some different kinds. So this was a asymmetric or a normal distribution, right? So one thing you want to call also is I told you the 68, 95, and 99.7 rule, right? So remember what that means is if we have a normal, oops, try to draw this better. If we have a normal distribution, and here is my z-axis, right, which tells me the number of standard deviations I am away, right? So right in the center of a normal distribution, this will be a z-score of 0, and then if we go one standard deviation out, this will be a z-score of 1. If we go 1 to the left, it'll be -1, right? Then we can get to 2, and then 3, and then -2, -3, right? And remember, in between each of these is one standard deviation, right, out. Right, so let me erase this. So then where this comes into play, right, is in between one standard deviation of our mean, which our mean is always at z-score of 0, there are 68% of our data in between here, right? So then remember, in between two standard deviations, there are 95% of our data. And then lastly, in between 3 standard deviations, we can expect 99.7%, right, in between 3 standard deviations. Right? So then this diagram here is just a little more accurate than this rule. So you can use this rule or you can use this diagram. They're about the same, right? These numbers are just easier to remember, right? 68, 95, and 99.7. Right? So then number 1, it says recall that this curve is a histogram, right? Just with really skinny columns, right? So that's what we're talking about. So i.e. the bins are very small, right? The bins are the class width, right? So it says what does the height of each column represent, right? So if I have a column here, right, what does this column represent, right? The height of it. So matching up over here, what does it mean, right? So this is what I would say. So we could say the height of each column gives the frequency, which are the counts, or relative frequency, which would be percentages of the data values in each bin, right? right? So what I'm saying is we can, on this side, this could be just a direct count, or it could be a relative frequency, which is you take what the count is and divide by the total number, and that gives you the relative frequency. Right, so this tells you the percent of the data that falls in each bin. So if we look on the left-hand side, notice these can't be counts, right, or frequency, because it's not like 1, 2, it's not a whole number. So since it's a decimal, right, like 0.1, 0.2, 0.3, 0.4, this means that that's relative frequency, right? So in this particular one, it would be relative frequency. Right, so what we could say to that effect is the normal distribution provided has percentages on the vertical axis. So the heights are giving the percentage of data values in each bin. Right. So it's a pretty good answer for number 1, right? So the number 2 says, in the normal distribution, what percentage of data fall below to the left of the mean, mu, right? Well, one thing that we need to recall from a normal distribution is that it's symmetric, right? And the mean cuts it directly in half. So if this cuts it in half, that means that 50% of my data will be this way, and 50% will be this way, right? So if you recall what it means to cut something 50% of the data, that's just the median, right? So in other words, the mu is going to be my median, right? Because that's what the median means. And then also if we think about the mode's the tallest bar. Well, the tallest bar is also occurring here, right? So that means that in a normal distribution, the mean is the median, which is also the mode, right? So this isn't always the case, but since we have a normal distribution, this is true, right? So this is true in a normal distribution. Normal distribution. So in a normal distribution, the mean, the median, and the mode all match. So for number 2, we would say 50%, right? So 50%. The next part says how many fall below +1 standard deviation, right? So in other words, how much of my data is here? Right? So there's a couple of ways you could do this. And an easy way, what I would do is, remember there's 100% underneath, so we could take 100% minus these parts. So this part is 13.6%, and then take away this percent, so minus 2.1%, and then this percent, minus 0.1%. Right, so if you plug this in, so 100 minus 13.6 minus 2.1 minus 0.1 gives me 84.2, right? So I got 84.2 here percent. Right? So let me write that a little clearer. 84.2% for that answer. So what this means is this is roughly, so this is really close to 85th percentile. Right? So like 85th percentile means that at this specific point, 85% of my data fall below it, right? So you may have heard that, like taking, like if you take like your, if you have a nephew or a child, if you take them to the hospital, or maybe maybe you've heard of other people talk about this, they might tell you the percentile of the height and weight and like head circumference of a child, right? So if you have a child that's 90th percentile in weight, that means that 90% of the U.S. kids are below below that child, right? So if you look at below plus 2 theta, right, it'll be similar. So we could still do 100% minus, but we're not going to subtract all these parts, right? So let me do some erasing here. So we want values that are below 2 theta. So that would be, right, so everything below here, to the left of here. We want to know what this percent is. So we could add all those up, but it's much quicker just to take 100 minus 2.1 minus 0.1, right? So we could take 100 minus 2.1% minus 0.1%. Right, so 100 minus 2.1 minus 0.1% is 97.8. So this is roughly the 98th percentile. Right? So remember what that means is, here's my distribution. If this value, if they're 98% below it, right? So if this is the 98th percentile. Okay. So if we do below plus 3%, then I would take 100% and then minus just the 0.1%, right? So if we look again back up at our diagram, what we're doing is we're including the percentage, the area in between 2 theta and 3 theta, right? So including all this. So now I just need to take 100 minus 0.1. Right, so if we do 100 minus 0.1, we get 99.9%. Right. Right, so going down to number 3. So number 3, it says, here are some fun questions. Make an educated guess, right? So what I would like you to do is you can pause the video here now and fill in A and B real quick before moving on, right? So you'll come up with some guesses. You're trying to see, what guess between what heights do 95% of U.S. women fall, right? So you'd want to figure this out, right? So maybe you think 50 and 60 inches, right? Whatever values you think. You come up here for females and then do the same for females, right? And we want 95% of my data in between here, right? So we want 95% in between here, right? All right, good. So then jumping down to number 4, it says, on the given normal curve, what percentage of data lie within 2 standard deviations of the mean from negative 2 theta to positive 2 theta, right? So if we're using the chart above, right, what you'll find is that that would be 2 standard deviations, or 95% lie in between 2 standard deviations, right? So from our chart above, you'll get that this would be approximately 95.6. Right, if you use their values, right? But remember, I already talked about and showed you that this is a much rounder, easier number to use, right? This is also an approximation, So you can be more and more exact, right? Different books, different statisticians are more and more exact about that value, right? So what we're noticing here is here's my mean, right? If we go one standard deviation out and minus one standard deviation, remember 68% is in between here. And then if I go 2 standard deviations out, right, then there's approximately 95% in between, right? So then now we're given these tables of heights in inches for U.S. women, females 20 years of age and older by race and ethnicity and age, right? So it's broken out between all of those things. And then we also have similar data for males, right? So then also we're given a definition. So it says the standard error of the mean is the standard deviation of the distribution of the sample means. The standard error can be estimated using a standard deviation from one of the samples. So standard error is approximately standard deviation divided by the square root of n, where n is the number of values in the sample, right? So standard error can be approximated by taking the standard deviation divided by the square root of n, right? That's what we're saying here. So we can use this to approximate. You can use like a statistical package to find this closer, but this is a good estimate for us, right? So it says caution. The standard error in the given tables was computed using a more sophisticated formula, so you cannot compute standard deviation from SE for these tables, right? So we have to use this fact, right? So this formula won't work quite as well because, as I was saying, we can use more sophisticated formulas or computer software to help us get standard error. So it's just warning that the values in here won't match exactly, right? They didn't use the formula, using more sophisticated software, right? So then now it says the standard error for women 20 years and over is given as 0.06 inches and can be interpreted using the fact that 68% of the data in a normal distribution will lie within one standard deviation of the mean as follows, right? So it says there is a 68% probability that the average height of women 20 years and over is 63.8 inches plus or minus 0.06 inches. There is a 68% chance that 63.8 inches is within 0.06 inches of the true average height or population average of women 20 years and over. And then the next bullet says there is a 68% likelihood that the average height of women 20 years and over lies in the interval from 63.74 inches to 63.86 inches. All right, so let me take a moment to explain what's going on here, right? After we read this. So standard error is, you can think of this as just another name. So this, think of it as another name for standard deviation, right? In essence. So standard error is a standard deviation when we're talking about the distribution of sample means, right? So let me go to a blank slide here and draw a picture. Whoops. All right. So when we have this normal distribution, right? When the population mean mu, right? So remember, we have what's called a population, and then we take a sample of the population, right? So remember, the population mean we call mu, and the sample mean we call x bar, right? And remember, in general, x bar is not equal to mu, but we use x bar to estimate mu, right? So x bar we use it to approximate mu, right? So remember, the general idea here is if we're doing a study, we can't possibly get data on the whole population, right? That's not very typical, right? So what we do in statistics is we get a sample mean to use that to estimate the population mean, right? But something else that's true is let's say if Tommy and Sam, right, are two students in our class. If they're trying to find the mean height of MTC female students, right? Then maybe Tommy gets a mean of, I don't know, 50, right? And Sam does the same study but gets a different sample and maybe gets a mean of 51 inches, right? So notice these are not the same, right? We can expect these to vary we could expect these to vary also, right? So it turns out that these means will also have will follow a normal distribution, right? So if we have a normal distribution and x bar is in the middle now, right, is what we're thinking. So what we know is that if we go -1 standard deviation here and +1 standard deviation, then there's 68% of my data in between those, right? If I go -2 standard deviations out, right, then now we're at 95%. 95%. Right? So this normal distribution also works for sample means, except since we're dealing with sample means, we don't use the term standard deviation, we use standard error, right? And we use standard deviation to get standard error, to estimate standard error, right? So if I go +1 standard error and -1 standard error, then I can still use the fact that 68% of my data will be in between here, right? This is called the empirical rule. And then if I go -2 standard error and +2 standard error, then I would also expect 95% still, right? And if I go -3 and 3 standard error, it'd be 99.7, just as if I do 3 standard deviations up here to -3 standard deviations, being 99.7% of the data, right? So using that idea, that's how we get these sentences, this interpretation, right? So right, so what this is saying is let me grab a different color. Right, so the average height of women is 63.8, right? That's what we were told, right? So if we look at the chart, 20 years old women, right here, right? 63.8, 20 years and over. So that's the mean. So this is 63.8. And then I can look up at the table and find the standard error, which is here, 0.06. So 0.06 is the distance in between x bar and +1 standard error. Right, so here there's a distance of 0.06. So if I take 63.8 plus 0.06, then we'll find this, +1 standard deviation. We'll find this value. That's here. Then if I take 63.8 and I minus 0.06, then we'll find this value here, right? So in our normal distribution, we have 63.8 in the in the center, right? This is my X bar. And then here, if this is +1 standard error, and here this is -1 standard error, then we can find what these values would be. Right? So 63.8 plus 0.06 would be what? 64. Oh wait, is it point? Yeah, 0.06. So 63.8 plus 0.06 would be what? 63.86. Right? And then over here, if we subtract, so 63.8 minus 0.06. Right, so I need to borrow. We get 4, right? 7. So 63.74, right? That will go here. Right? So using different words here, but just relate it back to what we already talked about with the normal curve, and it holds the same, right? So just when you see standard error, think standard deviation. When you think x bar, think mu, right? And then also remember that 68% of my data are in between one standard deviation of a normal distribution, or as in here, we use standard error, right? So within one standard error, there's 68% of my data in between here, right? So what this means, right, is if everyone else in the class, right, so maybe Ashley and Molly and I don't know, Travis, right? Maybe these are other people in the class. If they go out and find their own x bar, right, their own sample mean, we are 68% sure that their x bar will be in here, right? That's what this means, right? Within this range, in between these values. Right? So then on the next page, looking at number 5, right? It says estimate the following probabilities using the percentages and SE in the table. The probability that a random 20 to 29-year-old woman is over 66.9% tall, right? So we want to find the probability that our woman is bigger than 66.9 inches, right? So let's look at our table. So 20 to 29. So make sure you're looking at the one with females, right? Let me go ahead and erase this so we don't need this anymore. So we're looking at 20 to 29 years old, right? That's what was given. And we want to look for 66.9%. So that's, or not percent, but 66.9 inches, right, which is here. And this matches up with the 85th percentile, right? Right here. 85th percentile, right? So if you recall, right, if here's my normal distribution, and what we did is this value, x equals 66.9, is the 85th percentile, right? So what that means is that if we look at this part here to the left, this is 85% of my data will fall to the left, right? So 85% of data to the left. So what's the percentage of data that would be to the right, right? So if we take 100% minus 85%, we get 15%, right? So to answer this would be equal to 15%. We would expect 15% of the time our data to be above the 85th percentile, right? So then part B says the probability that a random sample of 20 to 29-year-old women has a mean height over 66.9 inches. So what's the probability that the mean height, so x bar, is greater than 66.9 inches? Right? So here you want to be careful. Here we don't want to just look at the percentiles in the chart. We need to use standard error, right? So let's look above, right? 20 to 29. Let's grab some information that we need. So I'll highlight this in blue, right? So we're still looking here, right? 20 to 29 years old. And we're still, so what we need to look at is the mean, and we need to know standard error, right? So let me write this down. So we know that the mean of the age group 20 to 29 years women, right, was 64.3. And the standard error is 0.12. Right? So let me draw our distribution, right? So here's my distribution. Here's x bar, which is 64.3 inches. Right, so this is x bar. So we're looking for 66.9. So 66.9 will be somewhere over here. And I want to know how much of our chart is shaded to the right of this, right? How much of our data is to the right of 66.9? So we're going to try to figure this out. So if I go 1 standard error, so plus 1 standard error over, that would be adding plus 0.12, right? So 64.3 plus 0.12 will give me the value for one standard error. So 64 plus 0.12 is what? 64.42, right? So that would be here, 64.42. So this is plus 1 standard deviation away. If we find for plus 2, right, then I would need to take 64.3 plus 0.12 plus 0.12, right? So this would be what, 64.54, right? So that would be here. So here is 64.54. Then if I go, let's say, so here, let's say this is plus 3. So plus 3 would be 64.3 plus 0.12 plus 0.12 plus 0.12. So if we add this all up, we get what? 64.66. 64.66, right? So let's think a minute about how much of our data is to the left of a standard error plus 3, right? So if we go back up to previous question, we already answered this, right? This was what? Here, this part, right? Where it says below plus 3 theta, right? So this is also the same as we found. This is also the same as below plus 3 standard error, right? Because remember, we're just standard error and theta really mean the same thing, right? Standard deviation and standard error. So there's 99.9% to the left of it, right? So what this gives us a hint at is that to the left of here is 99.9% of the data, right? So this way is only 0.1% of plus 3, right? Approximately. But our data point is well above 64.66, right? Even if we look at 4 standard deviations away, right? So 4 times 0.12 which would be 4 standard errors, right? Plus 4 standard errors. This would be what, 64.78, right? Which would be even even further away, right? So in essence, after doing this, you should come up with that there's essentially 0%, right? So the probability that we find a mean that is greater than 66.9 inches, right, is basically equal to 0, right? It's very, very small, right? Practically 0, right? Less than 0.1%. Right, so then number 6 is interpret the standard error for males 20 years and over in a sentence using 95% probability, right? So let's look up at our chart, our table, right? And now we're talking about males, so make sure you pay attention to that, right? We want to look at the males now. So the males 20, we want to look at the group 20 years and over, right? Which is here, and we're asked to use 95% probability by interpreting the standard error, right? So we need the mean and standard error to think about this, right? So let me write this down. We know that the mean here was 69.4 inches, and the standard error from the table was 0.13, right? For 20 years and over, it is 0.07, right? 0.07, right? Just find those values from the table that I've shown you above. So we want to use 95% probability in our data, right? So immediately you should be thinking of the 68, 95, 99.7 rule, right? The empirical rule. So we're looking at 95%. So what we're sure of is that 95% of the data will be within 2 standard deviations, or in our case 2 standard errors, right? So what we could say here, right? So first, let's find 2 standard errors, right? So what you'd want to do is find x bar minus 2 times your standard error, which is 0.07, and get this value, and then take x bar plus 2 times 0.07 and get this value, right? So x bar for us was 69.4, so I'm just going to substitute that in. 69.4. Right? So if we take 69.4 minus 2 times 0.07, that gives me 69.26. Right? So now we just need to do the same thing but plus. And we get 69.54. Right? So if you're a more visual learner, let me draw real quick so you can catch on to what I'm thinking. Right? So recall, if I have a normal distribution with a sample mean in between, right? Then here is 1 plus 1 standard error. Let's say here is plus 2 standard error. And let's say here is minus 1 standard error. And here is plus 2 standard error, right? So in between here and here, here and here, So not that. So in between there is 68%, right? So there's a 68% chance that our mean will be in between here, right? And then in between here and here, we can expect our sample mean to fall in here 95% of the time, right? So my mean was the 69.4, right? So this is 69.4, and then in between here, one standard error, which is 0.07. So I took times 2 because we want to do 2 standard deviations out, right? And I minus 2 because we want to go 2 standard errors to the left also, right? So then if I know these values are, then in this range, right? So this is 69.26, and this came out to be 69.54, right? So within this range, I can expect my, if someone else repeats my data, right, my study, I can expect their mean to fall within here 95% of the time, right? That's what this 95 means. So this is also referred to as the 95% confidence interval, right? We are 95% confident that our mean will fall within this, right? So I'm just going to make a note. So this is also called finding the 95% confidence interval. Right? So if I ask you to find the 95% confidence interval, this means the same thing, right? So what we could say is there is a 95% probability that the average height of males 20 years and over is 69.4 inches plus minus, oops, right, let me make this box bigger. Right, oh, we got a typo, too many A's. So there's 95% probability that the average height of males 20 years and over is, so we could even say this, right, is between so we got well, here, these values, right? So is between 69.26 inches and 69.54 inches, right? So you could say something like that. Right? So then number 7, it says recall that 85% of the data fall below +1 standard one theta, right? Standard deviation. So we can determine the standard deviations for men and women using the 85th percentile. Determine the standard deviation by subtracting the mean height from the 85th percentile for both the men and women 20 years and over. Right? So basically, right, what's happening is here is my distribution, right? Here we have the 50th percentile, right? Which again means 50% of my data is below, right? And this lines up with mu, right? And then the other item that we found is if we go +1 theta away, right? It's really close, right? To the left is about 85%, right? We looked at that previously. So this is the 85th percentile, right? Right? So if we want to find the standard deviation, if I take the 85th percentile minus the mean, then we can estimate the standard deviation, right? That's what is being set here, right? So we want to do this for both men and women, 20 years and over. So if you look on the previous page, right, and so you want to look for where it says 20 years and over, the first row with numbers, right, for men and women. If we look at the 85th percentile for women, so let's do this for women first, right? You will find that the mean is 63.8. Right? And then the 85th percentile, so if you look on the 85th percentile column, you'll find that the x value is 66.6. Right? So if I take 66.6 and minus 63.8, this is a way I can approximate the standard deviation. Right? So 66.6 minus 63.8 gives me 2.8. Right, so I can approximate theta to be 2.8. Right? And then we can do the same thing for men. So let me grab a different color. We'll do this for the men data sample. So for men, we're using 20 years and over row also. The mean is 69.4. And the 85th percentile, 72.6. So if I take 72.6 minus 69.4, right, this will give me a standard deviation. So 72.6 minus 69.4, you get 3.2. Right? So we found both of those. Right? Found the standard deviation. So 2.8 inches and 3.2 inches. And these are approximates, right? So approximately. Right? So that's the way you can approximate if you know the 85th percentile. So now number 8. Right, number 8 says to determine the z of your height, the z-score for your height. So remember, you need the equation z equals x minus x bar all over standard deviation, right? So let's say that you are a female, age, I don't know, 52, and your height is 50 inches, right? So what this would mean is we need to look at the table for female age 52 to find the mean, right? So we can find that by looking above, right? So if we go above, so I said what, age 55, right? 52, right? Whoops. So age 52 would be in this row, right? We want the mean, which is here, 69.5, right? That's my mean. Right, so the mean was 69.5. Right? Let me double check. 50, yes, 69.5. And then we found the standard deviation above. So we estimate the standard deviation above for females to be 2.8. Right? So we found this to be 2.8. And my height, or this female's height is 50 inches. So this is x. X is 50. So just plug this in to get z, right? So z would equal 50 minus x bar 69.5 all over a standard deviation of 2.8. Right, so 50 minus 69.5 divided by 2.8. Oops. You know this 69.5 seems very high, right? That is because I was looking at the male chart, right? So I'm a male, and I was mistakenly looking at the male chart. So we need to fix this, right? So let me fix this really quick. That way you can follow my example. So we need for the male, right? So for 52 years old and male, right, that follows to be, or female, that follows to be 63.9. So this should be 63.9 inches, right? For female, age 52, would be in between 50 to 59. So we'd have 50 minus 63.9 all divided by 2.8. So 50 minus 63.9 divided by 2.8. So we get this. Negative 4.964, so forth. Right? Alright. So you'll just want to follow this example for your specific height, right? So again, you're looking at the table, finding what your particular mean would be for your age, and depending on if you're male or female. And then x is just whatever your height is in inches. And then the standard deviation is what we estimated from number 7, right? So you'll use 2.8 for female and 3.2 for male, right? So number 9 says, use the standard deviation to determine your heights between which 95% of men and women fall. How close were your guesses? Right? So in other words, another way to write this is we need to figure out the 95% confidence interval for women and for men, right? So I'll do women here, and we're doing the before we were prompted with the ages, right, 20 to 20 or 20 and over, right? I believe. So this was question. Where was this? Number 3, right on page 44. Right. So for women, so first we need to find the mean. So for women, 63.8, right, for 20 and over. So the mean is 63.8. The standard error was or no, we're not. So we need standard deviation, right? Because here we're not talking about a distribution of x bar. We're talking about distribution of x, right? We're saying each individual women fall, right? So in other words, here's my distribution, here's my mean, and I'm looking at each specific person individually, right? So the standard deviation for women, right, we found to be 2.8, right? And in between two standard deviations is 95% of the data. So we need to take 63.8 plus or minus 2 times 2.8, right? 2 standard deviations. Right, to estimate this. So let me erase this, get some room. So if you plug this in the calculator, we take 63.8 plus 2 times 2.8. So this gives the range. See, I need right. So this gives in between the range of 69.4, and then we need to find what's over here, right? So if you want visual, here's x bar, here's plus 1 theta plus 2 theta, right? That's what I found here. And then this would be minus 1 theta, minus 2 theta, right, from the diagram. So to find the other one, we just need to subtract. So same thing, but subtract. Get 58.2. Right? So for women, right, we would expect 95% of women to be between 58.2 inches and 69.4 inches tall, right? And then we would repeat the same thing for men, right? So for men, right, similar diagram, right? But if we look above my mean, right, so if you look on the page with the chart, the mean for men, which is table 4.21, for 20 years and over is 69.4. And we found the standard deviation. We estimated that to be, I believe, 3.1. Is that right? 3.2. Right, so we got that earlier, 3.2. So then to find my 95% confidence interval, right, or which heights are between 90, where would we expect 95% of the heights of men to fall, right? So you would take the mean 69.4 plus or minus 2 times 3.2, right? Because for 95% we need to be 2 standard deviations. So similar thing here for males, except this is 69.4 in the center, and each one of these is 3.2 distance in between, right? So if we take 69.4 minus 2 times 3.2, we find the left part, right? So for the males, this would be 63, and then excuse me, for the right, the plus 2, it would be 75.8, right? So 95% of men, their heights would fall in between 63 and 75.8 inches, right? So it says how close were your guesses, right? So you can compare depending on what you guessed. So then the last question says, well, who is taller, a 6-foot woman or a 6-foot 6-inch tall man, right? So these come from different distributions, right? So we have a female distribution, but then we also have this male distribution that's a little different, right? We know they're different because their centers are different. Their x bar, right? Their mean. The mean height for women, right? We got above was 63.8, and the mean height was 69.4. So it's not really fair just to compare 6-foot tall woman to a 6-foot 6-inch tall man, right? Of course, if you just compare that way, the 6-foot 6-inch tall man is taller, right? But we have to consider this. that that females are generally shorter than males, right? That's what this means. The average of females is less than the average of males, right? So what's more interesting, what would be more interesting to do is determine, well, who's more of an outlier, right? Who's furthest away from their respective mean, right? So to be able to do this, you need to use z values, right? That's a standard value. So we use z values, remember, to compare things that come from a different distribution. Like, so before we looked at comparing SAT and ACT, right? So like here we have ACT and here we have SAT. So again, these have different means, different distributions, right? So we have to convert the z-scores to compare, right? They don't even overlap their score ranges, right? So let's do this. So a z of the woman, right, would be equal to, right, we take x minus x bar divided by standard deviation, right? So let's find these values. So remember, this is in inches and this is in inches. So this also needs to be in inches. So how do we convert 6 feet into inches, right? So if we take 6 feet times 1 foot is 12 inches, then, oops, these won't cancel out, right? We need to flip it. So we need 1 foot on the bottom and 12 inches on the top, right? So now the feet will cancel, right, using dimensional analysis, right? So now my feet will cancel, and I'm left with 6 times 12, right? Which is, what, 72, right? So this would be 72 inches. And so we also need to convert 6 foot, 6 inch tall man, right? So 6 foot, 6 inch is 6.5 feet. Right? So 6.5 feet, again, the feet will cancel. So 6.5 times 12, right? Will be what, 78? Yes, 78. Right, so this would be 78 inches. Right, so we'll need both of these values. So for the woman, we take this x value, right, because she was 6 foot. So we would take 72 minus, and then the woman x bar, the woman average. So we'll use 63.8, right, as before. And the standard deviation, right, so I'm looking here, right, the standard deviation for woman was 2.8, so we divide by 2.8 and we'll get a z-score. So if we take 72 minus 63.8 and then divide by 2.8, you get this. So 2.928571, so forth, right? That should be enough decimals to compare. So for the z value for the man, right, so he was 78 inches tall, and we need to subtract off the mean, which, so looking above, my mean was 69.4 for men, and the standard deviation was 3.2. So 3.2. So now we can get this z-score. So 78 minus 69.4 divided by 3.2, we get 2.6875. So the woman is taller, right? This z-score is bigger than this z-score, right? So in other words, the z-score for the woman is greater than the z of the man. So in respective to each distribution, the woman is more of an outlier, right? So here, if here is my distribution for a woman, right, so x bar for a woman, then if this is my z-axis, right, so here is the z value 2.68, right, for the man, and then over here would be 2.92. right? So here, this sticks out further away than whatever value would be here, right? So this female sticks out further away than the male would, right, within their respective distribution. All right, well, that ends this worksheet. If you have questions, make sure that you're reading the text and also emailing me.